Hello, my name is Maximilian Bandle, and today I will present to you our paper to partition or not to partition, that is the joint question in a real system. It is joint work with Jana Gicheva and Thomas Neumann. Imagine you're in a situation when starting off a new database system from scratch. You have to pick the right implementation to have optimal performance for all of the core components. So when picking, for example, the equi-join, which is a centerpiece for the overall performance, you're looking at the related work, what happened over the last decade. So for an in-memory database system, you come to the conclusion, oh, I should use a hash-based join. But then another question arises, how to exactly implement it or which variant to choose. Should I partition the tuples? Shouldn't I? When does it make sense to use a partition join as a booster? And in general, how do non-partition joins and partition joins perform inside of a real system? So that's exactly the question we answer in our publication here, and I'm guiding you through this talk. To have a quick recap and bring us all on the same page, we're just explaining some basics of the differences of non-partition and radix partition joins. A non-partition join, at least the naive variant, is a bit more straightforward. You have one single large hash table where you're inserting all the build side tuples into. After that's done, you probe the probe side tuples, looking into the hash table, potentially finding the join partner, and then returning the result to the next operator. The problem here is that it might be latency bound when the hash table is large, because in a large hash table, potentially each access to the hash table would lead to a cache miss because we have random access, and then we're latency bound because we have to wait on the data to arrive and we can continue processing the tuples. One way to circumvent that is, for example, to use prefetching, because with prefetching we can tell the processor in advance to already fetch this memory region, because we're going to read it from there in some tuples, and then when we actually read it from there, it's already present in the cache and we do not have a cache miss. That's possible in a database context, because having the whole probe side, we can peek and see, okay, we're accessing that tuple in 5 tuples from now, for example. Another way to reduce the number of cache misses is using a radix partition join. It revolves around radix partitioning, as its name giving, and it means we're having small cache-sized partitions, and they will get then into small cache-sized hash tables for the build side. Then, when we're having these hash tables, we are partitioning the probe side as well, so that we have pairwise partitions, one partition for the build side and one partition for the probe side. So now we can perform the join pairwise on this cache-sized hash table together with all the probe tuples. The nice thing here is, now that the partitions reduce the cache misses, because the working set fits into the cache misses, we do not have any cache misses during the actual join phase. However, that comes at the price of now being bound by memory throughput, because we have to read the build side and the probe side potentially multiple times, and we also have to materialize both of the sides in order to get the partitions to store the partitions to access them. So now looking at the difference between the implementations, let's also have a quick recap of the research. So over the last decade, in the beginning, we saw that hashing is faster than sort merge joins, and then it focused again on looking whether we should use non-partitioning or partitioning joins. Then our group did some research on how to tune a non-partition join inside of a code-generating database system, including how to scale it and be Neumann aware, for example. On the other hand, there also has been work on how to tune radix partition join, looking into more variants, and also comparing non-partition and partition joins, looking into the hardware consciousness as to prefetching and partitioning in general, and saying that it pays off. And also then looking at different architectures, different variants. But what nobody did so far is integrating both a partition and a non-partition join into a real system, and to tune the partition join to realistic workloads, rather than only using the micro benchmarks. And then, when having both of them tuned, to compare them against each other inside of the system and getting the conclusions for real work. So that's exactly what we are doing with our publication. To do that, we start off by using our code-generating database system, Umbra. It is the successor of Hyper, and thus it also has the Morsel-driven execution engine, and also similar implementation of an efficient non-partitioned hash join, which we are using here as a baseline. To add to that, we are having an efficient radix partition and join implementation we implemented for this paper. The join implementation is based on the ideas of ETH Zurich and Universität des Saarlandes, where we are implementing a model-driven partitioning scheme that is necessary because we cannot rely on a materialized build and probe site because we're inside of a real system. So we implemented our join as a materializing pipeline breaker, which means we materialize the build site into partitions and the probe site, and then we can start off a new pipeline, pushing the tuple to the next consumer by joining the build site pipeline and the probe site pipeline with each other. Having now both joins in the systems means we can perform arbitrary SQL queries and then either pick whether we want to join, for example, with an outer join using partitioning or non-partitioning, and we also integrated it with our query nesting framework, so it's fully usable inside of the system. But before we can jump right into looking at the TPCH numbers, we first have to look into whether the micro benchmarks are competitive. So we took the same micro benchmarks, the papers we got the radix partition join ideas from, and performed them after each other. And we saw that in the micro benchmarks, our code is competitive to the one from ETH Zurich. So that means the results we're getting from using a radix join are actually meaningful when looking also at TPCH. And now we come to the query, how does it work in TPCH? With the initial measurements, we saw that the non-partitioning join is 3 times faster than the non-partitioning and the radix partitioning join. And as expected, partitioning needs far more memory. So we were not able to finish all of the scale factor 100 queries within our memory budget. That means we are excluding those 3 queries from our aggregate results for now. While this did not match the conclusions we had from the micro benchmarks, where we could expect that a radix join, at least in some cases, would outmatch the hash join's performance. So we looked at the biggest differences between the 2 workloads. And in that case, it's how many tuples find a join partner. In TPCH, not every tuple finds a join partner. It's more like 10% of the partition tuples find a partner. While in micro benchmarks, every single partition tuple finds a join partner. That means no partitioning of a tuple goes to waste. While for TPCH, 90% of the tuples we partitioned are necessary and are dropped afterwards because they are not even accessed. And with memory bandwidth already being our major bottleneck for a partition join, we have to clearly do something against it, because when we're reducing the number of data, we overcome that memory bottleneck and we are faster again. And that's exactly what we did. We're introducing semi-join reducers based on Bloom filters, which was already an idea for having memory efficient hash joins, and also in our non-partitioned hash joins we have a semi-join reducer for really selective query. A semi-join reducer tries to avoid tries to prune potentially computation heavy tuples as early as possible in the probe site by peeking into the build site and looking whether it could qualify or not, having a cheap operation here. We are doing that by building 1 register block Bloom filter per partition. Afterwards, when we did that for each of the build sites partition, we can test the Bloom filter before we are partitioning the tuples in the probe phase. That means we are accessing first the filter, whether it could qualify, and drop the tuple in case if not. If it could qualify, we partition it. It greatly reduces the memory bandwidth at the price of some random access early in the probe phase. But since the Bloom filter is a lot smaller than the actual hash table, the random access is actually not too bad. That means in the performance of our Bloom filter partition join is far better than the original radix join for TPCH, and we are now competitive. And furthermore, we can also finish all the queries within our size budget. So we can now look into the queries in a more detailed analysis, because we right now replaced all the joins, no matter how their characteristics is, by a non-partitioned or a partitioned join. So going into a detailed evaluation, we looked at each individual join of all the queries in TPCH. To do that, we looked at all of the possible permutations and then fixed either one join being partitioned or non-partitioned and compared what the impacts are on the general overall runtime for the query. Here in that plot, you see the build site size as the x-axis and the probe site size as the y-axis. As expected, since partitioning aims at making it possible to fit the build site into the caches, it does not provide any benefits when the build site would fit into the caches anyway. So we can rule out the joins where the build site is smaller than the processor's caches. However, on the other hand, it doesn't mean if our build site is larger than the processor caches, we immediately profit from partitioning. So there have to be a lot more factors. And in fact, there's only one join that clearly benefits from using a Bloom radix partition join and gets a 30% speed up, while the other joins are at the same speed or most of them are getting slower. So we're really having to look at the important factors here to decide when to use partitioning and when not. And then to finally answer the question, when does radix partitioning pay off in TPCH and also in general? Digging a bit deeper here, we are first looking at the fourth join in query 5, because it's the one join where the build set is larger than the last level cache, but still has the most negative effect of using partitioning here. To the top right, you see another evaluation, where we looked at each of the joins of query 5 in detail, how much of an effect has it, whether we should use partitioning or not. In that case, we are 50% better off by not using partitioning here. The reason here, and also why the single join dominates the runtime difference here, is because the probe site is so large. It's more than 100 times bigger than the build site size, so it is the unfiltered line item table, which means we have to partition 20 gigabytes of data here. And partitioning 20 gigabytes of data here for the probe site means we have a large partitioning overhead, unlike the non-partition join, which only has to scan this probe site once instead of scanning it multiple times and materializing it into partitions. So we can say that the size difference should also be small in order for the radix partition join to pay off, and that it ideally be in the same order of magnitude. So we can also rule out the joins in that top part to be candidates for radix partition joins. But we still have to look around the cluster of query 22 here to reason why only one query here is faster. So we got into micro benchmarks and looking into a bit more detail. At first we looked at the different payload sizes. To do that, we used the same micro benchmarks we used earlier to ensure that we are competitive in performance and change other factors. In that case, we only change the size of the probe site size. We gradually increase it to see how the effects are. For radix joins, we clearly see that the throughput here, which is on the y-axis, decreases the larger the tuples get, because we also put more pressure on this memory subsystem. We get a larger probe site, and we are exactly the same problem we had earlier. The steps you notice here are because we are using streaming stores and which need aligned stores. For the hash join, however, the performance is still mostly influenced by the number of random accesses. And when having a larger tuple, it doesn't make a big difference because the random access is still the most costly thing here. And so we can see that the larger the payload size gets, the less beneficial it is for a radix partition join. This also influences how this join performs with a different pipeline depth. So for example, when looking at star schema benchmark queries, we are getting very deep pipelines. We're measuring it here in a measurement where we're saying, okay, we want to look at the throughput per join. That means we expect when we do one join, it is twice the speed as performing two joins, and so on. While this almost holds for the radix join, it is clearly not for the hash join, it is clearly not the case for the partition join. So this is the case mostly when having a star schema benchmark, because then we're having one central fact table which is connected to all of the other dimension tables. And the fact table gets larger the more keys we have to hold, because we have to hold one join key for each of the dimension tables. So in a radix partition join, we are slowed down because for each of the joins we have to partition the intermediate result and then go on to join the next, partition again, and so on. For hash-based join, however, we can build all the hash tables up front and then just have one single pipeline accessing all the hash tables after each other, so we could have synergies performing a lot of joins after each other. Having all those factors together, we can now look into what makes query 22 a good candidate for a radix partition join and to validate our findings. So to first look at the build size. The build size is clearly larger than our last level cache, so that makes it a good candidate. Then looking at the size difference, which is 1 to 11, which makes it almost in in the same order of magnitude. But considering the Bloom filter as well, which with a selectivity of 14.3% for our probe site, filters out some of the tuples from the probe site, we reduce the size difference to something far closer to 1.2, which is actually pretty close to having the same size build and a probe size. Then when looking at the query plan on the top, we see that the hash join is at the bottom, joining customers and orders. In query 22, that join is a non-exist predicate, where we don't have to transfer much information from customers or orders to the operators on the top. That means our payload size of the tuples is rather small with 12 bytes, also making it a great candidate for a radix partition join. Now with the pipeline depth of just one equi-join, because we are the only equi-join in that pipeline, makes it also a good candidate, and we can rule out the selectivity because we're using our Bloom filtered variant. To conclude that, all of the factors are pretty close to what's beneficial for a radix partition join, and thus we have the speed up, but it's only 30% speed up over the non-partition join implementation. And now we spoke about what's beneficial for a radix join, and now let's look at it in a table here to conclude the talk. So the different factors we are looking here, we're comparing them with the prior work, and afterwards how TPCH looks different to see why the performance in micro benchmarks from prior work and TPCH varies. So looking at the selectivity, the radix join performs best with 100% selectivity, which was also the case in prior work's micro benchmark. Then with the build size is also mostly larger than the last level cache and also beneficial for that partition join. With the size difference being also in a good range here, we also see a good performance for the partition joins. And then the payload size, because we're only partitioning integers here, is mostly smaller than 16 bytes, or sometimes even only 8 bytes for our whole tuple, including the hash key. And then since we're only looking at a micro benchmark, it's just one join, and you wouldn't see no synergies for having a non-partition join performing multiple joins after each other. Comparing that now to TPCH, we see that in TPCH we have a very low selectivity compared to the 100% in prior work, which is why we handle that with using the radix partitioned join with a Bloom filter. And in TPCH, the build sizes and the size differences also vastly different from prior work, because there we mostly filter a small query, a small build site, and look into with the small build site to a large probe site. And this leads into a big size difference and small build sizes, which are not that beneficial for partition hash joins. Since TPCH also involves some string processing, the payload sizes are also bigger than in prior work. And with having more complex queries, also more joins are there after each other. Another factor we didn't look into right now, but has also been considered, is skew. Skew is beneficial for the non-partition join, because in a non-partition join with more skew, you access some tuples more often, leading to beneficial effects when caching tuples. In a radix partition join, it's completely the opposite, because with skew, the partitions have different sizes, and it's more difficult to have the multi-threaded partitioning running with different sized partitions, since you need, for example, some kind of work balancing or work stealing to ensure that not one thread is doing all the work. While in TPCH we have no skew, it's pretty often the case in real world datasets, and it's also one of the reasons why the radix partition joins perform even worse on, for example, the join order benchmark, which bases on the IMDb movie set data. In summary, we identified 6 factors that influence the radix join's performance by measuring and comparing within a database system. We handle the selectivity by adding the Bloom filter, and we talked about build size and payload size. In the paper, you find more information about how and why size difference, pipeline length, and skew influence the performance as well. In general, partitioning is very sensitive to deviations from the beneficial workload characteristics, so the expected speedup is far lower than micro benchmarks could conclude, since they fail to represent the real world. So it's likely that you won't get any advantage using partitioning on most datasets. However, if you know your workload characteristics well and they closely resemble what's called beneficial in the table, you can still expect a speedup. Otherwise, prefetching is just way too good at hiding latencies. For that reason, we think that a non-partition join is sufficient for in-memory data processing, and we decided not to use radix joins in Umbra.